This is Solve It for Kids.
Hello, my amazing and curious friends. My name is Jennifer, the Dean of all things STEM and STEAM, and this is Solve It for Kids, the science podcast that gives kids and families a peek inside the real world of scientists, engineers, and experts as they solve problems in their jobs using creativity, cooperation, and critical thinking. And now please welcome to the show my podcast partner, Galactic Space Geek, Jeff Gagne.
Hello, Jennifer, and hello, listeners. Jennifer and Jeff are still on summer break.
Yes, we are.
So you get another best of episode, and you don't need to be a galactic space geek to love these topics.
Oh, absolutely. So what episodes are we learning from today?
The best of deep space.
The best of deep space. Jeff's favorite. Mine too.
Yes!
So these three you will be hearing from episode 201, How Do You Study Exoplanets with Dr. Dakota Tyler. Episode 210, What is the Deep Space Network with Rami Morgan. And episode 197, Where Could We Find Life in the Solar System? With Natasha Carr. So we hope that you enjoy all of these amazing out of this world episodes. Here you go.
How do you study exoplanets?
Ooh, how do you study exoplanets? This is a really great question and one that is so timely right now. We're going to have lots of fun chatting about this. Who is our guest today, Jeff?
Our guest today is the fantastic Dakota Tyler. He is an astrophysicist and science communicator at DT Star Kid.
Welcome to the show, Dakota.
Hey, thanks for having me. Excited to be here. Always love to talk science and planets.
Oh, we are thrilled. And we're talking about exoplanets, not just planets, exoplanets. But what I want to start with is, as a kid, were you always one of those people that went outside and looked at the stars?
I wasn't really a stargazer, but I distinctly remember in maybe second or third grade, we had the unit where we go over the solar system. And I remember this picture of Jupiter that just had the black backdrop of space. And I think I always refer back to that.
Oh, wow.
I love that you remember one image that sort of stuck with you. So was it the planet itself that stuck with you, or was it the black background of space with Jupiter just kind of hanging out, not being held up by anything?
I think it was the background. Like, Jupiter is beautiful and it looks really cool, and it's this massive, interesting planet. Yeah. But the blackness back there, it's like, what else is there? There's the Jupiter right here. But like, what else is out there?
Yes, exactly. So how did you get from there? And I mean, briefly, how did you get from there to being an astrophysicist? Because that's a pretty big leap.
There was a very winding path, because I think that was maybe the last time that I thought about space for 15 years.
Oh, wow.
I actually went to college and played football. So that's what I wanted to do. I wanted to go to the NFL, but I got injured and was trying to redirect and, figure out something else to do with my life. Right. And I got back into astronomy documentaries. And that's when I realized that there are more planets than there are stars. And it could be my job to study them.
And obviously, you just mentioned you got back into astronomy documentaries. Do you remember, was there something specific about there being more planets that caught your attention over anything else? There's asteroids, there's galaxies, there's black holes. What was it about
There's
that
dark
one
matter.
Thing yes. What was it about that one thing that you think caught your attention?
What's super interesting about planets is that I live on one. And so I'm sort of thinking what other possibilities could there be? What other life could there be? do we even have enough knowledge to guess, what other life could look like?
Love that question.
Oh, yeah, that's cool. Okay, so before we go all the way there, we're going to talking about exoplanets. So it's possible that some of our listeners don't know what an exoplanet is. Could you kind of explain what that is?
Sure. So it's short for extrasolar planet, and it literally just means a planet that is orbiting some other star other than the sun.
Right.
When you look up at night, all the stars you see also have their own planets, and we just call those exoplanets.
Wow.
Okay.
That's kind of the keyword these days in astronomy and space, isn't it? Looking for exoplanets?
Oh, yeah. The field is really booming right now.
Okay, that leads us right into our main question for this episode. I know it's a big answer. You start wherever you want, Dakota. How do you study exoplanets that are so far away?
Yeah, it's a great question because it's not as easy as it is to study some of the planets in our solar system, where you can actually look up at night tonight and see Jupiter in the night sky.
Yes. Yes.
You can't do that with these other planets. They're too far away. Even with the most high-powered telescopes, most of them are way too far away for us to actually see them. So you have to rely on these indirect methods and sort of see the clues that the planets leave behind.
Okay. So is that through, like, say, some of the bigger telescopes we have, like the James Webb or the Keck or something like that? Is that what you're using for your research?
Absolutely. So most of the planets that we know of have been found through what's called the transit method. So you imagine, staring at a star and you're just looking right at it and you don't turn your telescope away. And if you stare at it long enough, you may see a planet cross in front of it. And you don't actually see the planet cross in front of it. You just see the star get a little bit dimmer and then return to its normal brightness. And then you keep staring and you see that it happens again and again. Maybe it happens every 10 days. One way to explain that is you have a planet that is on a 10-day orbit that is doing this very predictable dimming of the star. This is called the transit method. And most of the planets that we found basically doing just that.
Wow.
Okay. And how many exoplanets? I know it's not, you don't have to give an exact number. I know that number kind of changes basically every day now. How many exoplanets have been discovered now?
So we've validated over 5,500, but this is a very small fraction of the perhaps hundreds of billions that are estimated to just be in our galaxy, not even other galaxies, like just the Milky Way.
That's insane. So, can you talk to us about how the James Webb kind of helped us see further out and see some of these exoplanets?
Yeah, so James Webb has the ability to see literally just about as far as we can see in our universe and see like early galaxies, but it doesn't really have the ability to see planets in those galaxies. Those are too far away. But what it can do is it can look at planets that are in the Milky Way, some planets that are in our galaxy, and it can actually study the atmospheres and start to tip us off about what type of composition, what type of molecules are in the atmosphere, which is really interesting, again, for somebody who's interested in life. Like, does this planet
I was
have
just going to say
that. Does it have H2O, carbon dioxide? Yeah.
Yeah, so isn't that like more like astrobiology, kind of where you're talking about how it's made and then whether or not life exists? Are astrobiology and astrophysics kind of getting melded these days?
Yeah, everything is sort of blending together. There's even astrochemistry. So you take, which is important, right? Because we need to understand like how these molecules are mixing and interacting. And then you have biology and astronomy. And so, astrobiology, astrochemistry, it's all like blending together now.
Whoa, that's cool.
Okay. You were just talking about how the James Webb Space Telescope can look at an exoplanet super far away, somewhere else in the galaxy. We can't see it with our naked eye. We can't even see it with our backyard telescopes, but it can see what the atmosphere is made of. Mm-hmm. Can you explain that a little bit? Because I want to make sure our listeners aren't seeing like it's not labeled. Like the
Right.
planet doesn't have a little sign that says, I'm made of carbon, hydrogen, and methane.
Yeah.
How does James
That-
Webb know what it's looking at?
Now, it would be nice if that was the case. That would make our jobs really easy. So if you think back to that transit method where the planet is crossing in front of the star, right? And it causes the star to dim a little bit. Yeah. And that's just because some of that starlight is literally being blocked by the planet.
Right.
Yeah.
But if you imagine on the edges of the planet, there is some atmosphere. It's like, it's not as rocky. There's actually some gas, the Earth has an atmosphere.
Right.
Sure.
And so what happens is some of that light actually passes through the atmosphere and doesn't get blocked by the middle of the planet.
Wow.
And whatever is in that atmosphere, whether it was carbon dioxide or methane, it would absorb some of the light from the star. And then the rest of those photons would come to us in our telescope. And we can kind of, really what happens is the planet atmosphere sort of leaves a fingerprint on that starlight. And based on that fingerprint, it actually is kind of like holding a sign saying, hey, there's water.
Hey, I'm here.
Hey, there's carbon dioxide. Yeah, because it's a unique fingerprint that only certain molecules leave.
What is the Deep Space Network?
What is the Deep Space Network? Well, this is a great question because I don't know that a lot of people know what it is or how important it is. So who is our guest today, Jeff?
You've got that right on the nose, Jen. Our guest today is the fantastic Ramey Morgan. She is a network operations analyst for the Deep Space Network.
Welcome to the show, Ramey.
Thank you. Hello, welcome. Can I have my title changed to, what was it, Galactic Space Geek?
Yes!
I'm emailing my manager right after this.
Absolutely.
Excellent.
Absolutely. So, good question, or good lead into the question. Since you were a kid, did you always want to be a galactic space geek?
Absolutely. Okay, I saw an episode of Magic School Bus where they go into the solar system and go to all the planets. And I was like, this is the greatest thing I have ever seen in my entire life. I watched it anytime. Well, we didn't have the recordings at the time, but I loved when it was on. I watched a ton of Magic School Bus. I had the book for the Lost in Space episode. I got all these atlases and encyclopedias and space books from the library. And my parents were like, I don't know anything about space. Have fun with these books. And I was like, have I got fun facts for you, Mom and Dad, every day at dinner,
That's
so
fantastic.
I've been interested in space as long as I can remember.
That's awesome.
Nice. So since you were so interested in space, what did you decide to study in school?
Never believe it, but I studied space. I got a major. I majored in astronomy, which is the study of space, right? So I took a bunch of different classes in all different types of astronomy because when you start getting higher up in space science and in astronomy, you start realizing that there are specializations. Someone who studies space doesn't just study space.
Right.
They'll study certain aspects of it, right? So you can talk to someone who studies stars for a living, right? And you'll ask them a question about a planetary process, right? And they'll go, I don't know. Because that's not their area of expertise, not what they do, right? If you talk to a planetary, geologist or a scientist who studies planets and you go, hey, how does this galaxy work? They're going to go, well, I can point you to a colleague, So, as you get higher and higher, you start realizing what aspects of space, you actually want to go into, not to mention things like aerospace, which is, how we get to study space.
Right.
Ways.
So what did you study? Like, which one of those did you pick?
I took a lot of classes, actually. I ended up going on both the astrophysics track, which is like the stars and galaxies and whatnot, and also the planetary science track. But I think I like the stars and galaxies a little bit more. I like, compact objects, things like black holes, neutron stars. So when a star dies, that's the best.
Right? Who doesn't like black holes? They are so cool.
They're so neat. I could go on and on about those.
I think we may do some of that.
Yes.
Okay, so in studying that, full disclosure, Ramey actually used to be the director of the Air Force Academy Planetarium, where I now work. She handed that job off to me to take this job. Ramey, what is a network operations analyst for the Deep Space Network?
Yeah, so let's break down network operations analysts. So an analyst is someone who analyzes, right? So you look at all of these different details of something, right? Take a bunch of details, a bunch of information, and you figure out what that means, right? So you analyze the details. So then network operations, so a network, that's a bunch of interconnected things, and then operations, how they work. So I look at how this network of things operates and figure out what we need to do to make it operate better. Yeah, so in this case, it's the Deep Space Network, which is a network of radio dishes. So it's how we talk to things in deep space. So they're these really big, they look like giant antenna dishes, these big bowls, right? In a few different locations around the world. There are 3 sites, and each of them have a few of these. And we use that network, right, to talk to things in what we call deep space. So that's like the moon and beyond. So if there's a spacecraft that is going to the moon or beyond, it is more than likely talking on our Deep Space Network.
Wow.
Okay.
So can you talk to us about what kind of frequencies these are using?
So they use radio frequencies. We refer to them as different bands. So we have so S band, K band, X band, Ka band.
And how far can they reach?
Really far. So the question of how far can something reach, how far can something listen, how far can something see with stuff like telescopes, because these are kind of like telescopes. We use them as telescopes sometimes too. It's not necessarily how far, it's how faint, right? So if you have something that's putting off a lot of energy, then you can see it much further away. If you have something that's putting off just a little bit of energy, then you can't see it as far away, right? So think about someone in another room whispering to you, right? You can't hear it as well. And then someone whispering to you from 2 feet away, you can hear that. But if the person back there was yelling, you could hear that, right? So it's not how far can you hear, it's how loud or how quiet you can hear. It's the same thing with these Deep Space Network, with telescopes, with your eyes.
That's a great explanation.
It really is.
Yeah.
That leads me to a question I've never even thought to ask before. So the farther out a spacecraft goes, does its signal need to get louder for the DSN to hear it?
Yeah, so there are a couple of things that you can do to kind of combat that. So with something like Voyager, right? Voyager's really, really far away. It's the furthest away spacecraft right now, right? So anything that it's sending back to us is really, really faint. You know, it's like, hey, I'm here. And so it was built a long time ago, and they didn't expect it to still be talking when it was way out there, right? It's really difficult to listen to it. So what we do is we use our bigger antennas. So we have 2 different sizes. We have ones that are 70 meters, ones that are 34 meters. So we'll use those 70 meters. Or we can also do an array, which is using multiple of them. So you can have a few different of the antennas are listening to the same thing, and you can pretend like you have an even bigger antenna by using multiple of them. So with that way, you can have something still sending a faint signal, but you have bigger ears.
That makes sense. Okay. Like so maybe this is a dumb question, but what I'm wondering is, does it have to be pointed in the right direction to hear it?
It does, actually, which leads to an interesting thing. I mentioned that it's in 3 locations. There are 3 locations around the world, right?
Right.
So there's one in Southern California, there's one outside of Madrid, Spain, and one outside of Canberra, Australia. And the reason we have these 3 different locations is so that every direction is covered, because the Earth spins around, right?
Right.
So when you're looking at something super far away, sometimes you're not on the right side of the Earth. But luckily, we have Deep Space Network on all points of the Earth. So you always have it covered. So the antennas also move. So they move around, they look up, they look down, they twist around. You actually do have to think about that too, because there's cables inside, right? So all this big wiring is in there. You can't just twist it all the way. Sometimes it'll twist and then have to come all the way back around to keep talking to a spacecraft.
Oh, so the wires don't get messed up.
So it doesn't get all messed up. Yeah, so they move around. It's really cool if you can see them moving too, because it's so large, you don't think it's something that should move, and then it just does.
Wow. That sounds cool.
Yeah, it really sounds cool to see.
We're going
to have to find a video to share.
Yeah, definitely do. It's so cool. It does also mean that you have to keep really careful track of where your spacecraft is. So part of my job, or my main job, is to work with different projects. So different spacecraft that are out there, I work with them to make sure that their spacecraft can talk to us and that we can talk to their spacecraft. So one thing we have to be, keep in mind is, where's their spacecraft going to be, right? So these projects, they send us all this stuff and they're like, hey, the spacecraft is moving in this direction at this speed and is coming close to this planet, and here's how it's going to move. We put it in our system to make sure that dish, the antenna, is going to actually be looking at it.
Okay, so that leads me to another question with the 3 different locations.
Mm-hmm.
Obviously, these missions are ongoing. It's not like they start and stop out there.
Mm-hmm.
So does a signal ever go from one station, get passed off to a next station?
Yeah, we have HASAs sometimes where you have the one antenna, so you might have it in Madrid, you've got one of them looking there, but then it goes that the spacecraft is below the horizon, so below what you can see in the sky, right?
Okay.
So the antenna can't look any closer at it. So what happens is there'll be a pass off, maybe over at Goldstone. There's another one who'll be waiting and ready to pick up the signal as it comes along.
Where could we find life in the solar system?
Where could we find life in the solar system? Oh my goodness, I can't wait for this conversation. Who is our guest today, Jeff?
Our guest today is the wonderful Natasha Carr. She likes to describe herself as being right in the middle of the Venn diagram between a planetary scientist and an instrumentation physicist.
Welcome to the show, Natasha.
Hello, hi.
We are so excited to have you. And I like to ask the first question, but I actually want you to explain first, what is an instrumentation physicist? What do you do with that?
Yeah, so it's a little bit of physics, a little bit of engineering, and a lot of in between. And so we design, we develop, we test, we break a lot of different types of instrumentation, which can be used for all sorts of different things. But personally, I work on space science and planetary physics. So my instrumentation will be going to different planets in the solar system.
Oh, that's very cool. So as a kid, did you always want to do stuff like this? Were you the one staring up at space and wondering what it would be like to be there or meet other beings from other planets?
Oh, most definitely. I think I was 3 years old when I said I wanted to be an astronaut, and now I'm almost 23 years old, and I'm still wanting to do that sort of thing. Yeah. Well, yeah, when I was 3, that was the main focus. I had a telescope. I was into all watched all the type of science shows and that sort of thing. And then when I was about 6 or 7, I realized that space was really dangerous.
Yes.
That was scary.
Good thing to learn.
Yeah. And so then my sights set on physics and on space science and what I do now. So it's been a pretty straightforward path for me. You know, a lot of incredible icons that I've always looked up to surrounding me. And then I'm now working with them, which is really cool.
Right?
That's
awesome.
Really cool.
Yeah.
And I bet if they're not already, very soon, they're going to be saying to other people, I work with Natasha.
I mean, I hope so. Definitely.
So I want to jump right in so we can eventually get to our main question. What is instrumentation physics?
Yeah, so it's looking at what scientists want to do, what engineers can build, and then developing the in-between bit. So people who might be geologists, chemists, biologists, anyone who's interested in asking questions about planets, and then turning towards engineers and saying, what do we have here and how can we make it better? Because we're the people that develop those ideas and make them become a reality. And then we build it and launch it.
That's fantastic.
Okay.
Yeah. So
that sounds very straightforward.
Well, there's quite a lot of wiggling in between. But, you know,
there are just a few things you have to figure out about how to create something to launch into space and make it work, right?
Mm-hmm. Yes. Everything from temperature to how much it's going to be shaken when it's launched, to how we can communicate with it and whether it might work in certain environments. Because even just the solar system, it's a tiny part of space, has so many incredibly dangerous environments to withstand.
Yes. And
our instruments can only withstand so much of it. So it's everything from it being destroyed to it working fine is how we have to think.
Okay.
Exactly. And then also, once it gets out there, you don't really have a whole lot of control over what it does or if something goes wrong, correct?
Not particularly. For example, my team worked on the Bepi-Colombo mission, which is currently on its way to Mercury. And we don't know when it gets there, when we turn it on, if it's going to do the job that it's designed to do.
So fingers crossed.
But yeah, there's always that gamble, and it's been traveling since 2018. So it's always that big hold your breath moment and cross everything that you can possibly cross to hope when it turns on, it shows us what we expect. Yeah.
Wow.
Very scary stuff.
Until then, there's really nothing sort of like it is officially off, or I've always kind of wondered in that safe mode that we usually hear NASA talk about or space scientists talking about, is the spacecraft sending anything like even a beep once a week to just say, hey, I'm out here? Or is there nothing until it's turn on time?
Yeah, it honestly depends on the type of instrumentation that you've got on there, what mission it is. How each mission varies quite wildly. I'll come back to Bepi. So a few months ago, it did its first Mercury flyby. So we turned on one of the cameras and it took some pictures, and we've got those back now. So we know that camera's working.
Yay.
But a lot of the other instrumentation, like the more complicated instrumentation that isn't a camera that you would possibly find here on Earth, is a little bit more complicated. And also you've got to think about the power needed to do that. A lot of the time, one of the massive restrictions is power. And so you've got to be able to serve that for when you definitely need it, when you get to your destination.
Sure.
Yeah, exactly. So also, you and I have been talking too, you're also interested in astrobiology. Can you tell everybody a little bit about what that is too?
Yeah, definitely. So astrobiology is a study of the origin, the evolution of life out in space. So anywhere that isn't Earth, really. And it's a really interesting subsection of science because as physicists, we can study it. As biologists can study it. Chemists often get really involved, geologists. So it's a really nice culmination of loads of different STEM subjects. And we can always evolve with that. And also, who doesn't want to find aliens, right?
Exactly, I do. I think it'd be interesting, yes.
And this is just the science behind it. And often people think, oh, well, it's going to be really difficult. But actually, it's not always just about finding life itself. It's about finding habitable conditions.
Right.
That's a little bit more possible with the instruments that we use.
Okay.
That's cool.
So with the instruments that you use, I kind of wondered, why don't all spacecraft include some sort of instrument that is searching for life? So
that's where it gets a little bit more complicated, because even with the missions that you look at now, like Perseverance, like Curiosity, that are on Mars currently, they aren't looking for life itself. They're looking for signs. They're looking for puzzle pieces that might lead us to look for life. So, for example, the rover that will be launched soon for the European Space Agency, the Rosalind Franklin rover, that's part of the ExoMars mission, that itself will be looking for the life itself. So a station that is able to look for life itself is a little bit more complicated because it needs to not destroy it. And a lot of instrumentation that we use now, if you use that instrumentation, it inadvertently kills the life that could be in the sample that you take.
Oops. I mean,
that would be bad.
Exactly.
I mean, but think about that for a minute. That's not something that most of us who aren't physicists think about, right? You're just like, oh, well, you find life and there it is. And but you don't think that the actual instrumentation that you're using might, I don't know, kill the life that you're looking for. That's intriguing. Can you give an example of that? Is it because of the heat? What would do that?
There's a few different types of spectroscopy which are used to look at chemical compositions that actually are quite destructive. So there's things like laser-induced breakdown spectroscopy, or LIBS, and that uses a laser to physically pummel away at a sample, and that isn't great for life. Sometimes,
no. For us either, for us humans either, I'm guessing.
Things like UV is often used, which again isn't great. We don't like UV. We get stunned from UV. So smaller microbes get completely destroyed. X-rays as well are sometimes used, which again, as we know, aren't great for us. So why would they be good for anything else? So honestly, it's about the scientific trade-off. So you have the geologists and the chemists saying, we need this type of instrumentation, so please send this. And that's a little bit more important for the questions that we're asking for this mission. Right. And then we have missions like ExoMars, where their sole purpose, or one of their sole purposes, is to look for evidence of life.
With topics like that, you really don't need to be a galactic space geek to want to learn more. So I hope you go listen to at least one of those full episodes, if not all 3.
Yes, absolutely. And you can find them on our website, solveitforkids.com, just like you can find all of our episodes there. And don't forget, there's a page of information for each episode, so you can even learn more. And if you liked our best of episodes, or you want to give us some comments, you can tag us on our social media. We're at KidSolve at Facebook, X, and Instagram. And we will see you next week, right, Jeff?
Yes, you will. We are still on break for the summer, but that means there's another best of episode coming. Until then, you'll hear Jen and Jeff on
Solve It for Kids.